Hi class, let's do some linear algebra. Last time we were exploring the concepts of an eigenvalue and an eigenvector, geometrically and otherwise. Today we want to connect it to other ideas that we know, and we're going to start with connecting it determinants, null spaces, singularity, etc. Theorem 31. Say A is an n by n matrix, and lambda some scalar, maybe a complex number, then the following are equivalent. A, lambda is an eigenvalue of the matrix A. B, A minus lambda I times the vector x is equal to the 0 vector has a non-trivial solution. The solution, of course, being the eigenvector corresponding to this eigenvalue. C, the null space of A minus lambda I is not equal to the 0 vector. D, A minus lambda I as a matrix is singular. And E, the determinant of A minus lambda I is equal to 0. This we will not prove. This is already encapsulated in the proofs that we've had before. Think on these and try and understand how they're connected. Okay. Let's talk about our characteristic polynomial. Our characteristic polynomial corresponding to lambda is simply the polynomial p sub a lambda is equal to the determinant of a minus lambda I. It turns out that if we explore what this polynomial is, we can start to understand some behaviors of our eigenvalues. The question that we're going to start with is, what is the leading coefficient? All right. We're going to start with the idea that we know that it has degree n in lambda when A is an n by n matrix. So let's explore this idea. So this polynomial is the determinant of A minus lambda I, which of course is just going to be the matrix A, A11 through A1n, A22 here, A12 here, A21, A22, A2n, all the way down to AN1, ANN. And since we have, of course, minus lambda I, along the diagonal we've got minus lambdas. Let's take the determinant by expanding along row 1. And remember, we're looking for the leading term, the lambda n term. Okay, so this determinant is going to be A11 minus lambda times -1 to the 1 plus 1 times the determinant of n11. Plus, I'm going to actually put all the rest into a sum. AI1 -1 to the I plus 1 times the determinant of mi1, as I ranges from 2 to n. Let's think about this for a second. The first term in this sum is going to be corresponding to this entry right here, A12. We're going to ignore the row and column that it's in, multiply by a power of -1, and multiply by the determinant of M12. Okay, so what you'll notice is that A11 minus lambda and A22 minus lambda are excluded. So this means that for all of these, similarly, they will not include A11 minus lambda, because it's in the row, or AII minus lambda, because it's in that column. Okay, so if we are in search of the lambda to the n term, we should not look here. Let's focus here and expand. All right, we have A11 minus lambda to times 1, and then we're going to look at the determinant of the matrix that's left, this determinant. All right, and it's going to start in its upper left corner. We are going to get A22 minus lambda times something plus some other stuff. Okay, we're not being very precise here, and we don't have to be, because what we're looking for is the lambda to the n term. It's going to be in here somewhere. And just to summarize what's happening, the only term in the determinant of A minus lambda I involving more than n minus 2 of the diagonal elements, as in the ones that include lambdas, is going to be the term that is straight down the diagonal. A11 minus lambda, A22 minus lambda, ANN minus lambda. This is a term that pops up in the determinant. It's the only one that involves more than n minus 2 lambdas. We're going to call this equation 1. Here's what I want you to take from this. The only way to get lambdas to the n is to start here and multiply all of the lambdas, etc. So the leading term of this polynomial is going to be -1 to the n times lambda to the n. This means that this polynomial looks like this. It's going to have a -1 to the n, and then it's going to be factored. Lambda minus some scalar, some complex number, lambda 1, lambda minus lambda 2, all the way up to lambda minus lambda n, where the lambda I are the roots, or the eigenvalues. This, if we distribute our negative signs, is going to be lambda 1 minus lambda, lambda 2 minus lambda, ... all the way up to lambda n minus lambda. This we're going to call equation 2. All right. What does all of that give us? Let's talk about what happens when we put in lambda is equal to 0. So let's just summarize. We've got the only term with more than n minus 2 lambdas is going to be A11 minus lambda, A22 minus lambda, ANN minus lambda. This is 1. And then we also have that PA lambda, the polynomial is lambda 1 minus lambda, lambda 2 minus lambda, dot, 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 lambda n minus lambda. This is 2. Question: what happens when we plug lambda is equal to 0 into 2? What we get is claim 32. All right, so we've got this polynomial where we plug in 0 for lambda. This is by definition the determinant of a minus lambda I, which is, in this case, is a minus 0I, which is the determinant of a. On the other side, if we use 2, plugging 0 in for lambda, what we're just going to get is the product of all the lambda n's. Remember, these are the eigenvalues. This means that the eigenvalues multiply to the determinant of A. That's going to be useful later. Okay? The next thing that I want to point out is just to recall this definition that the trace of a matrix denoted TRA is the sum of the diagonal entries. TRA is defined to be AII, I is equal 1 to n. An example, quick example. So if we've got this matrix 1, 2, 3, 4, the trace is equal to 1 plus 4, which is equal to 5. Claim 33 is about the relationship between the trace of a matrix and the eigenvalues. Claim 33, the trace of A is, well, it's defined to be this sum. We are claiming that it's also the sum of the eigenvalues. This might require some proof, so let's prove it. Okay, so we know the only term of the determinant of A minus lambda I to involve more than n minus 2 diagonal elements is the term in 1. So from 1, A11 minus lambda, A22 minus lambda, dot, 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 ANN minus lambda is the only term in the determinant of A minus lambda I to involve more than n minus 2 lambdas. All right, so we are looking for the n minus 1 degree term of PA lambda, the characteristic polynomial. How do we get this? Well, the only way to get an n minus 1 degree term of this is to, say, multiply A11 times the other lambdas, or to multiply the lambdas by A22, for example. And in this way, what we're going to get is the n minus 1 term is A11 minus n minus 1 of the other lambdas plus A22 plus dot 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 ANN negative lambda to the n minus 1. This is the sum of AII, I ranges from 1 to n multiplied by negative lambda to the n minus 1. Okay, that's the n minus first term as gotten from 1. From 2, well, what do we have here? PA lambda is equal to lambda 1 minus lambda sub 2 minus lambda, lambda sub m minus lambda. Okay, so the n minus first degree term, kind of multiplying similarly, is going to be lambda 1 times negative lambda to the n plus 1 plus lambda n to the negative lambda n minus 1. This is the sum of all the lambda I ranges from 1 to n, times negative lambda to the n minus 1. Setting these equal to each other, we have that the sum of the diagonal entries of a matrix is equal to the sum of the eigenvalues, because we set the coefficients. If the two terms, n minus 1 terms, look like this, then the coefficients have to be equal to each other. QED, end of proof. All right. What was all that about? Here's the upshot. Eigenvalues, they sum to the trace and they multiply to the determinant. Okay, let's use this. Let's do a few examples. Example. So we want to know what are the eigenvalues of A is equal to 1, 1, negative 2, 4. All right, we can do method 1, which we learnt previously. The characteristic polynomial is going to be the determinant of this matrix. We work this out. This is going to be 1 minus lambda, 4 minus lambda, plus 2. This is going to be lambda squared minus 5 lambda plus 6, which is lambda minus 3, lambda minus 2. So the eigenvalues are 2 and 3. And then we can do method 2. The trace of A is going to be the sum of the diagonal entries, which is 5. The determinant of A is going to be 1 by 4 minus 2 by 1, which is 4 plus 2, which is 6. The two eigenvalues, there will be as many roots as the degree of the characteristic polynomial, which is 2, because it's a 2 by 2 matrix. Two eigenvalues sum to the trace, 5, and multiply to the determinant, 6. There's actually only two numbers that do this, 2 and 3. Okay. We now have a few methods to find eigenvalues. Let's actually also find eigenvectors. Finding eigenvectors. This is a two-step process: eigenvalues, then eigenvectors. So, for example, for the example that we just did, we've got lambda 1 is equal to 2 is an eigenvalue. So A minus lambda 1I is 1 minus 2, 1, negative 2, 4 minus 2, which is negative 1, 1, negative 2, 2. We're actually going to row reduce this, and I won't bore you with the details. It says -1, 1, 0, 0. A minus lambda 1I therefore has rank 1, and by rank nullity, the rank nullity theorem, the nullity of A is going to be 2 minus 1, 2 minus the rank, which is also 1, which means the null space of A minus lambda 1I is going to be generated. It's going to have one vector that it spans it. Okay, so recall that row equivalent matrices have the same null space. This is lemma 26, if you recall. So we can actually find the null space for this matrix instead of this one. Sometimes it's easier to do. So the null space of A minus lambda 1I is going to be, just by looking at this, x, x. There's one vector that spans it, where x is R, otherwise known as the span of 1, 1. What does this mean? An eigenvector belonging to lambda 1 is equal to 2 is 1, 1. That means 1, 1, negative 2, 4, 1, 1 is 2, 1, 1. And that checks out. Here's an exercise for you. Find the eigenvector belonging to, find an eigenvector belonging to the second eigenvalue that we found, lambda 2 is equal to 3. Think on this. Talk to you next time.